Okay, so we are still in chapter 9, talking about thermochemistry. And we're going to look at a few more examples of thermochemistry applying stoichiometry to heats of reactions. So applying stoichiometry to heats of reactions. So we're going to go back to that problem that we had just used in the previous video with the combustion of sulfur and oxygen producing sulfur dioxide. And we wrote the equation like this: sulfur, S8, plus 8 moles of oxygen gas produces 8 moles of sulfur dioxide gas. And we said that the enthalpy change for this reaction was negative 2.39 times 10 to the third kilojoules. So this is a thermochemical equation. This amount of heat is evolved or given off when this reaction takes place. 1 mole of sulfur, 8 moles of oxygen, 8 moles of sulfur dioxide. So we can now use this heat of the reaction as a conversion factor for each of these molar amounts if we wanted to know more about how much of each of this was reacting, how much energy would be required to react a certain amount of any of these. So let's just look at an example. So here's a question. It says, you burn 15.0 grams of sulfur in air. How much heat evolves from this amount of sulfur? Okay, so essentially what we have here is we want to know how much heat is evolved from 15 grams of sulfur burning. What we have is this much heat evolved from 1 mole of sulfur burning. So we're just going to convert it to grams of sulfur from heat per gram for 15 grams instead of heat per 1 mole. So whenever you're doing stoichiometry, you always want to start with the value that you're given. So I'm going to say 15.0 grams. And then I want to convert grams of sulfur. I'm going to write out what we're going to do. We're going to go grams of sulfur to moles of sulfur. Moles of sulfur to kilojoules of heat. That's our pathway here. So I'm going to go from grams of sulfur to moles of sulfur. Remember, it's S8. So the molar mass of S8 is 256.5 in 1 mole. So now grams of sulfur will cancel. So now I have moles of S8. 1 mole of S8 evolves negative 2.39 times 10 to the negative third kilojoules. And remember, this negative sign is important because it shows the direction that the heat is moving. Is it being absorbed or is it being evolved? So now moles have canceled and my answer is just going to be in kilojoules. So how much heat, remember heat is Q. Remember, Q equals delta H. So you could technically answer this. Q equals negative 1.40 times 10 to the second kilojoules. Or you could say negative 140 kilojoules. Either way, your answer should have 3 significant figures. This number, negative 1.40, has 3 significant figures. If you're going to do it in standard notation and not in scientific notation, you need to put a decimal place after this number, after this 0, to make it significant. 140 without the decimal place just has 2 significant figures. So we're using stoichiometry, applying it to heats of reactions. So let's look at another one. This is kind of a long question, so I'm going to write it out. It says the daily requirement for a 20-year-old man weighing 67 kilograms is 1.3 times 10 to the 4th kilojoules. So I'm just going to write that out. A man, their daily requirement for energy is 1.3 times 10 to the 4th kilojoules. And then over here, say a woman, a 20-year-old woman, weighing 58 kilograms, their daily requirement for energy is 8.8 times 10 to the 3rd kilojoules. So this is how much energy a man needs. This is how much energy a woman needs for those specifications, which aren't important to this actual reaction. It says, if all this energy were to be provided by the combustion of glucose, how many grams of glucose would have to be consumed by the man and woman per day? And here's a reaction. So this is the combustion of glucose. Glucose is C6H12O6. It is a solid, plus 6 moles of oxygen gas produces 6 moles of carbon dioxide gas, plus 6 moles of water vapor. This is called cellular respiration. It is the opposite of photosynthesis. You've probably dealt with this reaction in biology. You'll definitely see it in biochemistry. This is cellular respiration. This is the process by which we take energy from the bonds in our food, glucose here, and we produce energy. So the enthalpy change here is negative 2.82 times 10 to the 3rd kilojoules. So this is the amount of energy that is evolved for 1 mole of 1 mole of glucose. A man needs this many kilojoules of energy. A woman needs this many kilojoules of energy. We want to know how many grams of glucose are we going to need to consume to make those amounts. This is 2 separate problems, but the process that we're going to take is going to be the same. We're just going to have different starting material. So I'm just going to write out the process that I'm going to take, and then I'll do it both with each man and woman. So we're going to go from the amount of energy that we need. I'm going to convert the energy to how many moles of glucose we're going to need. And then I'm going to convert moles of glucose to grams of glucose. I'm going to do that 2 times. Okay, so let's do the man first. So 1.3 times 10 to the 4th kilojoules. So I want to convert energy to moles of glucose. So I know that negative 2.82 times 10 to the 3rd kilojoules is in 1 mole of glucose. So kilojoules of energy have now canceled. So now I have moles of glucose. I want to go to grams of glucose. 1 mole of glucose has a molar mass of 180.2 grams. So now moles of glucose have canceled. My answer is going to be in grams. Grams of glucose that would need to be consumed to produce that much energy. So for the man, it's about 830 grams of glucose. So let's do the same thing over here for the woman. So I have 8.8 times 10 to the third kilojoules of energy. 1 mole of glucose is negative 2.82 times 10 to the third kilojoules for 1 mole of glucose. And then 1 mole of glucose is 180.2 grams. So this is going to give me about 560 grams of glucose. So something that you might be wondering is, well, what happened to this negative sign here? Obviously, we can't have a negative mass. We can't have a negative number of grams. Remember, this negative number here, it means that that energy is being given off. It does not make the number of grams negative. So you always need to be thinking about the signs of your energy and what it's telling you about the reaction, but also apply it only where it makes sense. If you used this and you said, well, the man needs to eat negative 830 grams, that doesn't make any sense. To give off that much energy, a negative amount of energy, technically this is a negative energy and this is a negative energy, so these would cancel and you would get a positive number. But just think about these signs and what actually they mean and what makes sense. So this is how we apply stoichiometry to heats of reactions, and we can use enthalpy changes as conversion factors.